Okay, moving on to Chapter 3 in Anton. Chapter 3 is about vectors, and Section 3.1 is about vectors in 2-space, 3-space, and n-dimensional space. So it begins with talking about geometric vectors, and these are just arrows. So it's called geometric vectors because you can draw them as pictures or as just arrows in 2D or 3D. And the length of the arrow encodes the magnitude. So here are two arrows of different lengths, and then the direction of the arrow encodes, some sort of directional information. And then we say two arrows are equivalent if they have the same direction and length. So all these arrows down here, they're equivalent because they have the same length and they're pointing in the same direction. In other words, they're parallel. And sometimes we'll say that the two vectors are equal if their associated arrows are equivalent. So we'll sometimes interchangeably use equivalent and equal when talking about vectors. Okay, so a vector is just an arrow, and as such, it has a starting point, A in this picture, and an ending point. Sometimes the ending point is called the terminal point, and the starting point is called the initial point. And then we write this notation A to B with an arrow above it if our arrow associated to this vector A starts at A and ends at B. And again, the same or equivalent vector can start at different points. Okay, as long as the vector has the same direction and same length, the two different vectors are considered equivalent, or sometimes I'll say equals. Okay, then these arrows or these geometric vectors can be added. And how to do so? Well, there's a couple ways. One is to use the parallelogram rule for adding arrows. So if you have two vectors v and w, again, that just means two arrows, and you want to add them, what you do is you make a parallelogram. So move v and w so that their starting points are the same. So right now up here, v started at this point, w started at this point, and well, looks like what I did was move this vector v over here by keeping the same direction and same magnitude. So we get this vector w here, and again, this vector w and this vector here are equivalent, even though they have different starting points and different ending points. Because they point in the same direction and have the same length, they're equivalent or equal. Okay, and so then make a parallelogram like so. One way to do that is to copy this vector w over here, and then v plus w, again, I'm trying to give a rule for adding two arrows or two vectors. And that is the vector that starts at this common starting point and ends at this point here. How did I find this point? Well, this is the end point of that parallelogram, or that vertex of this parallelogram. Another way to describe this point here is the triangle rule for adding arrows or adding vectors. Move w, so w is way out over here somewhere, and then move it so its starting point is the ending point of v. And then just follow the arrows, and that will give you the terminal or ending point of v plus w. So v plus w is the arrow that starts at this point, and then you follow v, and then follow w, and you end at this point. So that's what v plus w is, and the parallelogram rule shows that v plus w is the same as w plus v. Now we can also subtract arrows, and to form w minus v, that's going to be the same as w plus negative v. And negative v is the arrow that has the same length but is in the opposite direction as v. So here's v, and the negative v is same length but opposite direction. And so then we want to add this vector w and this vector negative v. Well, how do we do that? We move this vector negative v to the ending point of w. So in this picture, apparently what I've done is move w over here, and then followed w by negative v. And so this is what w minus v is. It's the arrow that starts here and ends here, shown in green. To review what was on the previous slide, so this is what w minus v is, and then v minus w is going to be this, the same length but the opposite direction. One way to kind of see this is that w plus v minus w does indeed give you v. Okay, so we've learned how to add two vectors, subtract two vectors, and then there's a third thing we can do, and that's multiply an arrow, again by arrow I mean vector or geometric vector, by a non-zero scalar. A scalar is just a number. I'm going to call that number k, and it's going to give an arrow with the same length, the same direction, but not the same length. So instead, the length is multiplied by k. So, for example, if k is 2, then here's a vector v, an arrow that starts here and ends there, and then 2 times v is an arrow that same direction. It doesn't have to start and end at the same at the points where v starts or ends, but its length is multiplied by 2. Okay, so to make all this stuff about arrows and directions a bit more precise, we can choose a coordinate system. That you might be familiar with the xy coordinate system. And so points in the coordinate system have coordinates, the x coordinate and the y coordinate. When we're in 2 dimensions, it'll have 2 coordinates. In 3 dimensions, points will have 3 coordinates. So for example, this vector v here, we could think of it as beginning at a certain point, say 0, 0, and ending at another point, and that point will have coordinates 3, 1, for example, in the xy coordinate system. And so this is this vector v. It starts at 0, 0, ends at 3, 1. Let me draw in the xy coordinate axes. So this is the origin, here's the y-axis, here's the x-axis, and then this point way out over here is maybe at 10, 1, and alright, I have another vector that starts at 10, 1 and ends at 13, 2, and this vector here, this arrow, is equivalent to this arrow here. Sometimes I'll say that these two vectors are equal, even though they start and end at different points. So that's a little bit funny thing about vectors, is that we're working up to an equivalence relation. But anyway, why are these two vectors the same? The vector here and the vector there, why are they equivalent or equal or the same, even though they're clearly different? It's because their direction and length are the same. Why are they the same? Well, this vector this vector out here goes over 3 units and up 1 unit. You can see that by taking the change in the x coordinate. So 13 minus 10 is 3, and 2 minus 1 is 1. So that's why I've written that v is equal to this 3, 1, this vector here. So this might be a little strange that we've got these two vectors that are clearly in some sense different, but they're also the same. And what we want to do is basically just record the 3, 1. That will make things easier. And implicitly, the initial point of such a vector would be 0, 0. So we have a vectors or a bunch of arrows, and then we can simplify this by making an assignment to R2. And a vector v, we assign it, in the particular example, just a pair of numbers, in the case of vectors in 2D, the 3, 1. And implicit in this is the vector that starts at 0, 0 and ends at 3, 1. So this is the correspondence between arrows and points in R2. Again, R2 is just the xy coordinate system, and a vector v, you then assign to it 2 numbers, the x and y coordinates, and these are called the components. Some Sometimes it's called the x component, the y component of a vector. Now, what if the arrow doesn't start at the origin, but starts at some point p1 with coordinates x1 and y1? This is the notation for a point p1 that starts at x1 and x1 comma y1, and then a point p2 that has coordinates x2 and y2. So suppose we've got this vector here that starts at p1, ends at p2. The vector we want to assign to it is not x2 comma y2, because this vector here doesn't start at 0, 0. Instead, what we want to assign it to is x2 minus x1. That's going to be the x coordinate, if you will, or the first component. And then the second component is going to be y2 minus y1. Hopefully the example on the previous page shows that when I had this vector that started at, I think it was 10, 1 and ended at 13, 2, it's going to be associated or equal to the vector that starts at the origin and then ends at 3, 1. So to associate this vector to 3, 1, what we want to do is take the change in the x coordinates and the change in the y coordinates. So this is this correspondence between arrows that are kind of all over the place and points in R2. They correspond to vectors that start at the origin and end at the point that they've been identified with in R2. Okay, here's a simple example. Find the components of the vector p1 to p2, where p1 is the point 5, 2, so that starts somewhere here, and then p2 is the point 6, 5, so that's somewhere over here. And so p1, p2 is the vector that starts at p1 and ends at p2. And the components of this vector are simply, you take the change in the x coordinates, so 6 minus 5, and then take the difference of the y coordinates, 5 and 2, and you get 1 and 3. So that's the answer for what the components of this vector are. Elements of R2, R3, or even Rn are called vectors. So what is a vector? Well, let's stick with the case of R3. That's just a triple. An element of R3 is just a triple of numbers. So here's a specific example, 5, 2, 1. And we use these parentheses, not square brackets, to denote a vector. And this symbol here means an element of. And this is one particular element of R3. The R refers to the real numbers. So the numbers in here are real numbers. They could be fractions or irrational numbers like pi. And similarly, Rn is just a list of n numbers. So v1, v2, all the way up to vn. And each of those numbers is an element of R, the set of real numbers. So v1 is just a real number, like 5. v2 is another real number, like -0.5, and so forth. So here's what a vector in n space, sometimes we call Rn n space or R3 3 space. And so an element or a vector in Rn is just a list, an ordered list, the order matters, of n numbers. So if we've got a vector v and a vector w, the definition of adding these two vectors is we simply add their components. So v1 plus vw2 is the first component or the first number or entry associated to this vector v plus w, and I need to give n numbers, and here's the first number, here's the second number, and here's the nth number. Similarly, to subtract two vectors, we subtract their components like so. And then another operation is scalar multiplication. So k is a number, not a vector, a number, and v is a vector. So that means v consists of n numbers, v1, v2, all the way up to vn. And then we're defining this what's called scalar multiplication. You take a scalar, multiply it by a vector, and we just simply multiply each component by that scalar k. So k times v1 is a product of two numbers, so that's another number, and so forth. All right, let's do an example. So let u be the vector -3, 1, 2, and v be the vector 4, 0, -8. And the question is just simply find 6u plus v. Okay, so first of all, 6 times u, the 6 is only multiplying the u, it's not multiplying the v. So we need to find 6u first. So here's what u is. 6u then is multiply each of these numbers by 6. That's exactly this definition here of scalar multiplication. Multiply each of the components by, in this case, our value of k is 6. So 6 times -3 is -18, 6 times 1 is 6, 6 times 2 is 12. Okay, then v, let's just copy that down here. And then 6u plus v, vector addition is done component-wise, as simple as it could be. So -14 plus 4 is, -18 plus 4 is -14, 6 and 0 is 6, 12 and -8 adds, or -8 adds to 4. And that's the answer. Let's do another problem, a completely different problem. So now let u be this vector 0, 1, -4, v be another vector 5, 0, 1, and the question is find a vector x in R3 such that we have this equation holds. So, and it turns out that vectors follow a lot of the rules that hold in algebra. So what we do to solve this problem is we can start with this equation and add u to both sides. So this negative u turned into this u here, and then I subtracted x from both sides. So this 3x minus x turned into 2x. I apologize for doing a few steps a little bit quickly without writing them down. Okay, and then now I'm going to multiply through this equation by the scalar 1/2, and so I'm just left with x here, and then on the right hand side I get a 1/2 times this vector, and then now I substitute in these values. U was this vector, v was this vector. 6 times this vector is I multiply all the components by 6, so 5 turns into a 30, 0 and 1 turn into 0 and 6. Then I add these two vectors component-wise, so 0 and 30 is 30, 1 and 0 is 1, -4 and 6 is 2. And then scalar multiplication multiplies each component by 1/2, and that's the answer.